Welcome back to Wickerson Studios. We're actually going on to the number 5 script in a minute called intervals, but we will go back to actually take a look at the real line. And I built a small model for the real line here, which is the in the Cartesian plane, basically dealing with real numbers that are expressions in decimal form. Real numbers can be represented geometrically as points on a number line, which is referred to as the real line, which is what I've generated here in the top view. Like I said, once you get a handle on a lot of this, you'll start turning it into 3 dimensions and get really interested. There's a little script here, and I'll highlight a few of the points within it, and the lines within it, and the vectors within it, and show you how we can map that with a 3D text tag as well. And then down here, just a little bit of information about properties of the real number system, fall in 3 categories: algebraic properties, which most people know, and there's a little bit of information here on that: added, addition, subtraction, multiplication, and division. Then there's ordered properties that say they are ordered, and there is what's referred to as completeness. We'll talk about a little bit in a minute. They follow the usual laws of arithmetic laws, and then they follow the, once again, I was just mentioning what the ordered properties refer to in completeness states that there's no holes within this line. Now, there's 3 special subsets. One that everybody knows is the natural numbers, not the natural numbers, the integers, which have 0, plus, and minus, those extending the natural number set, and then there's the real numbers, which state that as long as n is equal to 0, you can represent it by two real numbers, m over n. And then you'll see that there's a little bit of issue that happens here with rational numbers terminate or end in a string of repeating digits over and over in time, like 1.33333 repeated, for instance. And the exception is that the rational numbers do not possess the completeness property. For example, square root of 2, which cannot be represented as m over n with n not equal to 0. And so that provides us an opportunity for studying the limits of calculus. So let's go take a look at the script. It's not too hard, pretty basic. What I went in and I used the same thing that I've been using consistently through here just to build this line out from one end to the next. I'll just shrink it a little bit. It's a little hard to see. Make my grasshopper a little smaller and then extend my Rhino window. You see that basically we're placing within these points, extending from, you can make this line bigger, you can make it shorter, but you want it around 3 so you can visualize it. And I pushed it in the positive and negative direction from 0, set up a domain through a range. This time I'm actually using the domain and the range, and I guess I should build this tool out for you. But those are quite long videos, and I just encourage people to get a hold of these on my GitHub page and play with them. I'm creating those points and producing a polyline because you don't need a nerves curve, it's just a straight line. Grabbing the start and end of those lines, I put a vector and put that little arrow visualization on the end with a vector display. And you can toggle that on or off to unitize it, because otherwise it will repeat the full length of the vector. Unitizing just makes it a unit of 1, which is kind of nice to deal with. What I then did was I took all of my data, and this is kind of a poor programming way of doing it, but I thought let's grab -2, -1, -3/4, 0, 1/3, 1/3, and then I went into the expression nodes actually. Had a little fun using the square root of 2. I also thought a way in the expression node of typing it as use this little chevron. I don't remember what it's called. 2 to the exponent -1/2, which is actually the square root of 2, or you can just type in square root because the program's smart enough. Same thing with pi. You can use the expression node pi, but you can also just type in the penalty tool pi. And then you get an output of all those values, and those values are actually put and set to these points. I put a little circle on these points, so I made it solid so you can see it. I rotated the plane of actually the 3D text. There's a little bit of fancy footwork here, which I liked. Otherwise, if I didn't rotate it, 0.5, let's say if I took this all off here, grabbed this one and took it to disable, you'll see that the number tags, well, nothing works with that 0. I need it to default to, maybe that's not a good example. I need to set up a little default of rotation 0. Now, if I rotate it to 0, you'll see those numbers kind of go across each other. So that's why I put that -5 in there, and I just enable that. So that keeps some control of that. So I should break this down. It actually did a pretty interesting thing where the concatenate up with these lines in here. These lines have actually been scripted in the panel tool, and they're rotated as well. And I put them through a 3D tag. So I'm pretty proud of my little model. And when you get good at making these models and thinking them through, you're really working in 2 dimensions and having a really firm understanding of the model you want to make. So I'm not going to make this long video. The script is there if you're interested. I haven't put it up on my GitHub yet. repository through my Patreon. I think this is all information people can find in any calculus book. So if you're getting hold of it and you're interested in this, please continue. The next thing I'm going to look at is intervals, which are finite subsets of something that we can actually start dealing with data. So this file is getting pretty large. It's actually getting pretty good. We started with the ideas of calculus. We went through creating parametric points, parametric curves, and trigonometric curves. I then talked about functions, limits, and continuity. I did a little model of the falling rock, which I think people enjoyed. And now I'm on to just dealing with the real line. I'll take that off, and like I said, I'll deal with intervals after this and solve some very specific equations. I would like to build a model for closed and open intervals, and that might be very nice with concatenation tools and the proper parentheses. I've never seen anything like that online. And then we will get into grafting coordinates, and we'll start dealing with ellipses and circles, which I know a lot of people have been waiting for because I've gone through the points, the curves, polylines, the curves, and of course we're waiting to get to these circles. I just thought it was essential to have a look at a little bit of the math behind the here in calculus as to why we would want to do this and what's the purpose of it. Thanks for watching.